So, hello everyone. So, we are going to start the last lecture of week 7. So, this is different configuration of bioreactor. We are calling as a special bioreactor. So, quickly if you remember, in the last lecture we discussed this batch operation, fed batch operation and continuous operation with the free cells, free enzyme, immobilized cells and immobilized enzyme. In addition, we also discuss another continuous mode of operation, that is a plug flow bioreactor with all 4 variations. Now, today we are going to discuss some special bioreactor, particularly bubble column, airlift, fluidized bed, packed bed and trickle bed reactors. In addition, we will see the summary of bioreactors required for animal and plant cell culture. So, what should be the quality of an ideal bioreactor? The first thing, it should be stable to combat shear, heat and if there is any reactivity by the product, because your product may be reactive and it should not react with the bioreactor material. It provides control and sterile environment, because many times we go do pure culture fermentation. It should facilitate the mass, heat and oxygen transfer. It combats the mechanical failure and performance fluctuation to ensure the consistency in different batch of production. It should be versatile, so it should support the production of different products. So, we are having a bioreactor system and so we should be able to produce different kind of metabolites using different producer strain and different substrates. Energy efficiency, it should be designed to utilize less power. Yeah, sterility, this is very important. So, there should be provision for in situ as well as the ex situ sterilization, and it should, very important, it should comply with this FDA and good manufacturing practice regulations if you are producing the pharmaceuticals. These are very important for their further this utilization, and it should be non corrosive, and at the end it should not get degraded and release any toxic substance in the media. So, when we discuss what are the factors that influence the performance of bioreactor, so first comes the reactor configurations. Second, what is the scale? It is the lab scale, pilot scale or industrial scale, and industrial scale also what is the typical size, whether it is in the thousands of liter or it is a lakhs of liters. And then mode of operation. We have already discussed different mode of operation, in which mode we are operating it, and last one is what is the optimized condition, what is the temperature, what is the pH, what is the duration, what is the other requirement of micro and macronutrients. So, now if you see any bioreactor, they are going to have different components, and that components we can classify based on the structural component. It includes vessel, head plate, base and supporting frame. There will be mechanical component like agitator, baffle, spurger and shaft. There will be functional component like sensor. You can have the temperature sensor, pH sensor, dissolved oxygen sensor. There will be valve for the inlet and outlet. There will be sampling port to take the sample at different time intervals, and there will be probe where this sensor can be connected to the bioreactor, and there are control panels where we can have different type of controller like SCADA and this proportional integrated derivative controller and different softwares, and it should allow sterility and cleaning system like cleaning in place, steam in place, and if it is not possible for thermal sterilization, there should be provision for this air/steam filters. You can go for filter sterilization. The CSTR we will be not discussing in detail here because we have briefly talked about CSTR, and more detail about the CSTR will be discussed in the next module of where we will be discussing this aeration part. So, in brief we can see there is a mechanical component, that is a motor mechanical component, there is this impeller mechanical component, sparger mechanical component, and buffer. These are the mechanical component. And in addition we are having the inlet and outlet provision. This is a port for the, if we want to add the acid base for the pH adjustment, or anti-foam, foaming to control the foaming. There is inlet for the compressed air, and this is a filter here. Further, if you require to control the temperature, so there should be this inlet and outlet of cold or hot to control the temperature. If it is the exothermic, then it require cooling. If it is endothermic, it require the heating. So, this is the jacket where we circulate this heating or cooling fluid. And when you will see there is a total reactor volume, and this is the some head space here, and this is the working volume. So, for the bioreactor we need to give some head space for the foaming and some other disturbances in the bioreactor. So, there is a typical ratio of working volume as compared to total volume of bioreactor, and this is the base of bioreactor. Similar to this plug flow bioreactor also we will not be discussing. This is a kind of a tubular bioreactor. So, there is no variation in velocity, concentration, temperature or reaction rate along with the axis reactant is coming and your product is getting out. And what is the factor? Here is the length. So, with increase in the length we receive the conversion from the reactant to product. Yeah, so this is important. Now we will be seeing few special bioreactor. First one is the bubble column. As we see, there is no mechanical agitation here. So, it will minimize the power requirement for the agitation. There is air supply and there is sparger and there is a gas outlet. So, aeration is done by gas sparging, and that also helps in the mixing part as well. So, there are some aspect ratio S to D, height to diameter is maintained in the range of 3:1 to 6:1. So, as you see there is particularly there is no soft and this mechanical agitation. So, it requires low capital cost, it lacks the moving part and satisfactory heat and mass transfer performance, and of course, it is less energy intensive. So, we can have this homogeneous flow. So, this occurs only at the low gas flow rate. In that case, all bubble rise with the same upward velocity. There is a little or no back mixing of the gas phase, and at the same time there is a limited liquid mixing as well. But we can also have the heterogeneous flow. It occurs at the higher gas velocity. In that case, bubbles and liquid tend to rise up the center of the column, then further they go for the downflow of the liquid occurs near the wall. So, in this way we can just see there is a circulatory pathway here and here, and there is a back mixing of gas as liquid circulation entertains bubbles. So, we can operate this bubble column in a homogeneous flow as well as in heterogeneous flow. So, mostly it is applied for the production of Baker's yeast, beer, vinegar and in wastewater, in biological wastewater treatment. Next is a further modification in the bubble column, that is airlift reactor. So, in the airlift you are having this sparger where we are going to pump the air, but there are certain variation here, because when you are purging the air, so there is a riser tube, you can see the riser tube where you are purging the air, it will go up and further it will having the circulatory mixing. So, it will go like this, it will come and it will go like this, and then further there is a gas outlet as well. Now, we can have this internal loop vessel as well as the external loop vessel. So, if you are having this sparger here, then it will go and it will circulate like this, and if you are having a sparger to the outside of the riser tube, then this will go and this will keep on circulating like this. So, this is the internal loop, and further there is a possibility to have the external loop where a riser tube is almost, you can see there is a close and gas is going out like this, then it has to circulate along with the this space available due to the riser tube. So, it is going like this, then it is getting circulated. So, you can say this is a kind of a external loop because of the position of the riser. So, here the pattern of liquid flow are more defined owing to physical separation of upflowing and downflowing streams. Typically, S to D ratio is 10:1, and here mixing is better in the external loop as compared to the internal loop vessels. And then we should be able to calculate what is the KLA, mass transfer coefficient. It is depending on the superficial velocity. Velocity to the power 0.7. What are the typical application? This is used in the production of single cell protein from methanol and gas oil, in municipal and industrial wastewater treatment, and it is also used in the plant and animal cell culture because it exerts the less shear, and plants and animal cells are the shear sensitive cells. Next, we are going for the another configuration, that is the packed bed. So, you are having a column which is packed with the catalyst or the biological agent, and there you are having a pump to recirculate the liquid. Now, the cells are immobilized, or you are having a particulate biocatalyst, and it can operate both in the upflow and downflow manner. So, it is going from here to here, and then it is getting recirculated like this. So, this is a schematic of upflow. It is coming from here, then further it is getting air, it is getting, because there is no air supply here. So, aeration is done in a separate vessel here. After the aeration, again it is recycled, and in this way there is a continuous recycling of medium. So, if air is spat directly into the bed, then there are chances of the bubble aggregation, and which produces the gas pocket between the particle and this causes the flow channeling or maldistribution of the media. So, here that problem can be avoided because we are not directly the spurging bubble here, rather we are ensuring this aerations in a separate vessel. And this is used for the production of this aspartate and fumarate, conversion of penicillin to 6-amino penicillinic acid, and also this resolution of amino acid isomers. So, another configuration is fluidized base. So, rather than the totally being packed, you are going to have this packed with less amount of biocatalyst or biological material. The packed bed are operated in the upflow mode with the catalyst beads of approximate size and density. The bead extends at high liquid flow rate. So, when along with the flow, beads will go up and slowly their velocity will keep on decreasing, and when it will reach to the top, the velocity, upward velocity will be 0, then again it will drop down. So, in this way it is velocity is set in such a way that it should, biological material should not cross the bioreactor. So, in this way the clogging of bed, which is the problem with the packed bed bioreactor, as well as the flow channeling, can be avoided if you use this fluidized bed bioreactor. So, this is also used in this waste treatment with sand or similar material supporting mixed microbial population. It is also used in the brewing and production of vinegar. So, for this we are going to use this flocculating organism. They may be flocculants of only organism, or they are attached on certain solid support. The further modification of the same is the trickling bioreactor. This is another variation of the packed bed, where we are supplying this liquid from the top or bottom, mostly from the top, and you are sparging with the gas, and here what is happening, this your liquid or your media, it trickles, as the name suggests, it trickles, and then it is interacting with this biological agents, and in this way this whatever substrate is getting converted to the product. Most common use for this is the aerobic wastewater treatment. Now, with this we will quickly see this for this animal cell culture and the plant cell culture, what are the requirement or what are the consideration for bioreactors. So, first this animal cell culture, what are the features? They are the shear sensitive, and second feature here is for animal cell culture is they mostly grow on the support, or you can say they are the anchorage dependent rather than growing in a suspensional culture. So, for that one option is you can have the microcarrier. One example is the Sephodex. The cell grow in the monolayer, or they can also grow in the multilayer on the microcarrier. You can also have the hollow fiber bioreactor. In that case, cell grow outside of the tube, a nutrient pass through the tube from the inside. There are some challenge like uncontrolled and unmixed environment, and get this high cell concentration. For example, this hybridoma demonstrated 5 to 50 milligram per liter antibody. We can also use the stir tank bioreactor, but only thing we need to be careful with the RPM, because these cells are shear sensitive. So, RPM is very low, kept very low, 10 to 30 RPM, and typically the bubble column are the most preferred, or the airlift bioreactor. Next is this perfusion system. What is perfusion system? Where we should be able to simultaneously separate the product and byproduct, because many times the byproduct may be toxic. So, simultaneous cell cultivation and product concentration, and we are able to remove the bioreactor. So, this is also very important for the animal cell culture. So, we need to have a separator after the fermentation, so that we can quickly separate the product and byproduct can be removed. Similar to animal cell culture, we will quickly see the bioreactor configuration for plant cell culture. So, if it is suspension culture, so we can use this mechanically agitated tank and bubble bioreactor. This, as I told earlier, also airlift reactor is suitable for this animal and plant cell culture, and we can also have a special impellers which exerts less shear. We can also use the cell immobilization approach. It follows a two approach. First cells are grown, then immobilized, and once immobilized, the condition for product formation are optimized. Other option is if they can be entrapped in the hollow fiber membrane or in the alginate and other beads. And for organ tissue from the same plant may give good yield, so that we can go for the shoot culture or the submerged culture using the bioreactor configuration what we have discussed so far. So, with this I will stop here. So, today we discussed the configuration of different type of bioreactors, and further we have seen that what are their key features in terms of aeration, in terms of shear, in terms of their applicability, and in the last slides we discussed what are the special consideration for animal and plant cell culture. Thank you so much.